Okay, in this video we're going to be reviewing for what will be on the fourth exam that will cover all of Chapter 4, and your fourth exam will be on Monday, November the 30th. That's the Monday after the fall break and Thanksgiving holiday. Okay, and there are 19 problems that will be on your fourth exam, and you will have a help sheet that will assist you with some of these problems that will be on the exam. Alright, let's start off with problem number 1. Here you're going to approximate each number using a calculator and round your answer to 3 decimal places. Alright, so in part A we got 3 to the power of 2.4. I'm going to do this on another page. This is review for exam number 4, problem number 1. In part A, you got 3 to the power of 2.4. And we want to enter this in the calculator to 3 decimal places. Okay, here we go. Alright, we type in the 3. There is a caret key on the right side, right below the clear button. You press that, that's going to be for your exponent. And then type in the exponent of 2.4. And then go ahead and press enter. So here you'll get 13.96661017. But we have to round this off to 3 decimal places. So here, the third number after the decimal point is a 6. Next to it is another 6. So this 6 will make the 6 in front of it a 7. So it'll be 13.967. So 3 to the 2.4 power will be 13.967. Part B, e to the power of 3.4. Part B is e to the power of 3.4. Okay, on the calculator, to access the e, we have to press the second key, which is the blue key, or the yellow key, depending upon which calculator you have, and then your LN button for e to the x. So second, LN for the e, and then type in 3.4, and then hit enter. So it'll be 29.964100005. But to 3 decimal places, we round that off to 29.964. So e to the power of 3.4 will be 29.964. Okay, so that's problem number 1. Problem number 2 on your review sheet is this. Find the accumulated value of an investment of $10,000 for 5 years at an annual interest rate of 8%. If the money is Part A compounded quarterly, Part B compounded continuously. Okay, now let's identify what we already have in that particular problem here. Alright, in this case here, we have an investment of $10,000, so that's going to be the principal, or what P is, $10,000. For 5 years, that's the time. The interest rate is 8%. But 8% as a decimal, you drop your percent sign, move the decimal point 2 places to the left. That will be 0.08. Or you can take the 8 and divide that by 100, and that will help you change that percent to a decimal, because percent means per 100. Alright, now let's go ahead and use that to answer parts A and B. In part A, you're told that the money is compounded quarterly. if it's compounded quarterly, that means that there are 4 compoundings in a year. So that means your n is going to be equal to 4. And we have to use this formula for quarterly compounding. As a is equal to p times 1 plus r divided by n raised to the n times t. Okay, so here we just substitute those values into this formula here. Your p is going to be $10,000 times 1 plus r, that's going to be that 0.08 in decimal form, divided by n, which was 4. And that's going to be raised to the n times t. Your n is 4 times t, which was 5. Now, what I would do here is go ahead and multiply that 4 times 5. That would give me 20. So here, this would be a is equal to 10,000 times 1 plus 0.08 divided by 4. That whole thing is raised to the 20th power. And all of this can be typed into the calculator. So in this case, I'll type in 10,000, and then left parentheses, 1 plus 0.08 divided by 4, close parentheses, use the caret key for the exponent, which is this button right here, and then type in your exponent of 20. And then you can go ahead and press enter. Now, since we're dealing with money amounts, we always round to 2 decimal places. So 14,859.47396 to 2 decimal places will be $14,859.47. So this will be the amount, the accumulated value of an investment of $10,000 for 5 years at 8% compounded quarterly. $14,859.47. So that's part A. Part B, compounded continuously. So now you want to find out what the accumulated value is of that investment at 8% compounded continuously at a time of 5 years. Well, anytime you're doing continuous compounding, you have to use this formula. A is equal to P times e to the RT. A is equal to P times e to the RT. So in this case here, your A, we substitute the P with 10,000 times e to the R, that's going to be 0.08 times t, which is 5. Now this expression we can type into the calculator to find out what our accumulated amount is going to be. So here I'm going to type in 10,000. Now for the E, if you recall, second and ln for the E, second ln. Okay, that's second and ln. That will give you the e to the exponent. This exponent we can type in as is, 0.08 times 5. Now for those of you who have the older calculator, you might have to close your parentheses around that 0.08 times 5. And then go ahead and press enter. Now again, we're going to round this off to 2 decimal places, so this will be $14,918.25. That's going to be the accumulated value of a $10,000 investment for 5 years at 8% compounded continuously. Alright, so that was problem number 2. Okay, problem number 3 is you're going to write the equation of log to the base 6 of 216 equal to y in its equivalent exponential form. So here we have log to the base 6 of 216 equaling to y. Now I want to write that in its equivalent exponential form. Okay, well, there is this rule that says if you have log to the base b of, let's say, x equaling to y, and I want to write it in its equivalent exponential form, I do this. The subscript for the log is your b, that's your base. What's after the equal sign or what's in front of it, that's going to be the exponent for that base. So it'll be b to the power of y equaling to x. The x is whatever is immediately after the log. I'm going to apply that rule to this particular problem here. So for log to the base 6 of 216, in this case here, the 6 is the base, that's the subscript for the log. That y will become your exponent for that 6. So it'll be 6 to the power of y, and that has to equal to whatever is immediately after the log, 216. So in its equivalent exponential form, log to the base 6 of 216 is equal to y is equivalent to 6 to the power of y equaling to 216. So this is your exponential form for this logarithmic equation. All right, problem number 4. All right, in problem number 4, we got to write the equation 7 to the power of y is equal to 200 in its equivalent logarithmic form. So we got 7 to the power of y equaling to 200. And we need to write that in its equivalent logarithmic form. Well, in this case here, in logarithmic form, you have the log to whatever that base is of, and I say the answer is whatever is after the equal sign, that's always equal to whatever your exponent is from that base in exponential form. So, if I want to write 7 to the power of y equaling to 200 in logarithmic form, then I need an log for the log. This 7 is going to be the base. The y, which is your exponent for the 7, that's going to go after the equal sign. This 200 right here will go immediately after the log. So in this case here, we're going to have log to the base 7 of 200 equaling to y. So this will be your equation from exponential form to its equivalent logarithmic form. Okay. Problem number 5 is to express the expression or evaluate the expression log to the base 2 of 64 without the use of a calculator. That's log to the base 2 of 64. We want to find out what that missing exponent is going to be. Anytime you're evaluating a logarithm, you're always evaluating an exponent. So I'm going to let x equal to this. And then I'm going to convert that into its equivalent log exponential form. It's already in logarithmic form, so we need to convert it into its equivalent exponential form. So here this will be 2 to the x equal to 64. Now I'm going to write 64 in exponential form with a base of 2, because I know 64 is a multiple of 2. So let's start off by dividing 2 into 64. And keep dividing 2's until we can't divide anymore. So here if I divide 2 into 64, that's going to go 32 times. And then divide 2 into 32, that's going to go 16 times. Divide 2 into 16, that's going to go 8 times. Divide 2 into 8, that's going to go 4. Divide 2 into 4, that's going to go 2 times. So as you can see here, 2 is used as a factor 6 times. So in this case here, when I rewrite 2 to the x, that 64 would be 2 to the 6. Because 2 is used as a factor 6 times, so 64 would be 2 to the 6. Now, if these bases are the same, then I can set these exponents equal to each other. So here, this will be x equal to 6. There's a rule that says if the bases are the same, you can set these exponents equal to each other. So here, x equals 6, that's going to be the missing exponent that I was trying to find. So I can conclude that log to the base 2 of 64 is 6. And that's because 2 to the 6th power will give me 64. Alright, let's move on to problem number 6. Alright, in problem number 6 it says here, evaluate or simplify each expression without the use of a calculator. Evaluate or simplify each expression without the use of a calculator. So in problem number 6 you got log of 10 to the power of 7. And I want to find out what that's going to be equal to. Well, there's a property for logarithms where if you have log of 10 to whatever that exponent is, that's simply going to be that exponent. Okay? Log of 10 to the power of x is equal to x. So here, log of 10 to the 7 would just simply be 7. And that's the answer right there. So here I'm just applying just the properties of common logarithms, where if you have log of 10 to whatever the exponent is, it will be just that exponent. Alright, number 7 is ln of e to the 9th power. Now here, I'm using a property of natural logs where ln of e to whatever that exponent is, again, will be that exponent, because ln and e are inverses of each other. So, ln of e to the 9th power would just simply be 9, just applying that property for natural logarithms. And it's an inverse property of natural logarithms. Alright, number 8. Here I got e to the ln of 7x to the 3rd power. Now, this is another one of those properties for natural logarithms here. If you have e to the ln of whatever x is, it's simply going to be x, because e and ln are inverses of each other. So in this case here, e to the ln of 7x to the 3rd will just simply be that 7x to the 3rd. And that's again because e and ln are inverses of each other. Okay. Alright, problem number 9. This is where we use the properties of logarithms to expand each logarithmic expression as much as possible. And wherever possible, evaluate logarithmic expressions without the use without using a calculator. So here you have 4 of those. Now in this case here, you're going to have the log to the base 8 of 13 times 7. Log to the base 8 of 13 times 7. Notice we have the log of the product of those two numbers. I can expand that using the sum of their individual logarithms. So in this case here, log to the base 8 of 13 times 7, expanded using the product rule, it will be this. Log to the base 8 of the first number, which is 13, plus log to the base 8 of the second number, which is 7. And that's all there is to it. Because I can't evaluate 8 to what power that would give me 13, nor can I evaluate 8 to what power that would give me 7. So we just leave it like this. Log to the base 8 of 13 plus log to the base 8 of 7. Alright, number 10. We have ln of e to the 4th divided by 8. ln of e to the 4th divided by 8. Notice we got the natural log of the quotient. So here we need to apply the quotient rule. Where you have the natural log of the quotient, we can expand that as the difference of their individual natural logarithms. So here, ln of e to the 4th divided by 8 would be ln of the numerator, e to the 4th, minus ln of your denominator, which is 8. So we got ln of e to the 4th minus ln of 8. But we're not done yet, because I can do something with this ln of e to the 4th, because ln and e are inverses of each other, where ln of e to whatever this exponent is that exponent. So ln of e to the 4th will simply be 4. So I'm going to have 4 minus ln of 8. Okay. So that final answer will be 4 minus ln of 8. So here you may have to evaluate a logarithmic expression as far as you possibly can, like in this one here. Now number 11. Alright, number 11, you have the log of n to the negative 6. The log of n to the negative 6. Here we got an exponent here, so we need to apply the power rule to this particular problem here. What the power rule states is this. I can take this exponent and put it in front of the logarithm. So here, that negative 6 will go in front of the log of n. And that's all there is to it. So this will be negative 6 times the log of n. Problem number 12. This one you're going to have to use a combination of those three properties for logarithms. Here we got the log to the base 8 of 64 divided by the square root of x plus 1. Now, as you can see here, we got the log of the quotient right off the top. So let's apply the quotient rule by expanding this as the difference of their logarithms. So log to the base 8 of 64 over the square root of x plus 1 will be this. Log to the base 8 of your numerator, that's 64, minus log to the base 8 of the denominator, that's the square root of x plus 1. Now let's evaluate log to the base 8 of 64. We have to think of 8 to what power that would give us an answer of 64. Okay? So in this case here, I know 64 is a multiple of 8. And 64 can be broken up as 8 times 8. So 64 in exponential form will be 8 squared. Because 8 times 8 does give me 64. Now here the bases are the same, so these exponents can be set equal to each other. So that means x equals 2. That's the missing exponent there. That's what log to the base 8 of 64 is. So here log to the base 8 of 64 will simply be 2 minus log to the base 8. Now that square root of x plus 1, I'm going to rewrite that radical in its equivalent exponential form. That's going to be the x plus 1. Since it's a square root, that exponent for the square root will be 1/2. So x plus 1 raised to the 1/2 is the same as the square root of x plus 1. Now in this last term here, I can apply the power rule by taking that 1/2 and putting it in front of the log. So this will be 2 minus 1/2 log to the base 8 of the quantity x plus 1. Now keep in mind you have to keep that x plus 1 in the parentheses because you're taking the log of the entire expression x plus 1. So my final answer there will be 2 is equal to 2 minus 1/2 log to the base 8 of the quantity x plus 1. Okay, so all of that represents problem number 12. All right, number 13 is this. You're going to use the properties of logarithms to condense the logarithmic expression 5ln of x minus 9 minus 2 ln of y. Write the expression as a single logarithm whose coefficient is 1. Wherever possible, evaluate the logarithmic expression without using a calculator. So here we got 5 ln of the quantity x minus 9 minus 2 ln of y. Well, notice we got coefficients in front of the natural logarithms, so those coefficients will become exponents. So we're using the reverse of the power rule on each of these terms here. That means that this 5 will become the exponent for x minus 9. So I'm going to have ln of x minus 9, and that's raised to the 5th. Minus, now this 2 will be your exponent for the y. So the ln of y squared. Now, I have the minus sign in between these natural logarithms, so I'm going to be taking the differences of their natural logarithms. I can condense that using the quotient rule. Okay, minus sign means the difference of the natural logarithms. We can condense that as the natural log of the entire quotient. So I'm applying the quotient rule here. So the ln of the numerator is x minus 9 divided over x minus 9 raised to the 5th. The y squared will be your denominator. So that will be condensed as ln of x minus 9 to the 5th divided by y squared. Okay, so that's problem number 13. So here we have to use a combination of the power rule and the quotient rule. All right, problem number 14. In this case here, we're going to use common logarithms or natural logarithms and a calculator to evaluate log to the base 14 of 87.5 to 4 decimal places, and you're told to use the change of base property. So here we got log to the base 14 of 87.5. So that means we can use log to the base b of m And this is using common logarithms where the numerator will be the log of whatever you're taking the log of in the first place, divided by the common logarithm of our subscript, which is your b. Or you can use this. Use natural logarithms, where log to the base b of m is going to be ln of the argument of m divided by ln of that subscript, which is b. Either way, you're going to get the same answer. I'm going to go ahead and use common logarithms here. So log to the base 14 of 87.5 will be this. The numerator is a log of what's immediately after that log, that's 87.5, divided by the log of the base here in this problem here, that's going to be 14. And then I'd use my graphing calculator to enter this in to find out what that value is going to be. So in this case here, we're going to go ahead and press the log key, which is next to the number 7 key on the left-hand side, and then type in 87.5. But you have to close the parentheses around the 87.5, because you only want the log of 87.5. And then that's divided by the log of 14. Close parentheses. And then press enter. And you'll get 1.6944075999. But to round that off to 4 decimal places, that would be 1.6944. So log to the base 14 of 87.5, applying the change of base property to 4 decimal places, will be 1.6944. Okay. All right, problem number 15 deals with exponential equations. 15 and 16 are exponential equations. 17 and 18 are logarithmic equations. Starting with number 15, you're going to solve the exponential equation 3 to the 2x plus 1 equaling the 27 by expressing each side as a power of the same base, and then equating the exponents. So you're told what to do right here in that particular problem there. So here we got 3 to the 2x plus 1 equaling the 27. Well, notice that 27 is a multiple of 3, and I can write 27 as 3 to some power. Well, think of this. 27 is 3 times 3 times 3, or 3 to the third. So, if I write 3 to the 2x plus 1, that's going to be equal to 3 to the third, because 3 times 3 times 3 does give you 27. Now, the bases are the same. I can go ahead and set these exponents equal to each other. So that means I can set that 2x plus 1 equal to 3. Okay? 2x plus 1 is equal to 3. I can go ahead and solve this equation for x. So to get that 2x by itself, I'm going to subtract 1 on both sides. So that means 2x is equal to 2. And then solve for x, I'm going to have to divide both sides by 2. That means x is equal to 1. So x equals 1 is the solution to that exponential equation. Okay. Alright, problem number 16. Here you're going to solve the exponential equation 3e to the 5x equal to 1977. Express the solution set in terms of natural logarithms, then use the calculator to obtain a decimal approximation correct to 2 decimal places for the solution. So we've got 3e to the 5x equals to 1977. Well, the first thing we need to do to solve this equation is to get that e to the 5x by itself. We're multiplying it by 3, so let's go ahead and divide both sides by 3. So I'm going to have e to the 5x, and that's equal to 1977 divided by 3 will give me 659. So I have e to the 5x equaling to 659. And then the next step is, since e and the natural logarithm are inverses of each other, what I'm going to do here is take the natural log on both sides of this equation. So I have ln of e to the 5x equaling to ln of 659. Well, I also know that ln of e to whatever this exponent is that exponent. So ln of e to the 5x will simply be 5x. And that's going to equal to the natural log of 659. Okay, again, ln of e to whatever that exponent is that exponent. That's one of those properties of natural logarithms here, or inverse properties of natural logarithms. Now I can get the x by itself. I'm multiplying it by 5, so I need to divide both sides by 5. So this will be x is equal to, I'll rewrite this as ln of 659 divided by 5. And we're going to approximate this. And by the way, that ln of 659 divided by 5, that's your exact value. We're looking for the approximate value. So we're going to press the ln key, and then 659. Then you want to close your parentheses around the 659. Because you only want the natural log of 659. And that's going to be divided by 5. And you'll get 1.298144707. To 2 decimal places, it'll be 1.30. Because that 8 will make that 29 a 30. So it'll be 1.30 approximately. So that's the approximate value of x for this exponential equation. Okay. All right, problem number 17. Here you're going to solve each logarithmic equation. Be sure to reject any value of x that is not in the domain of the original logarithmic expressions. Give the exact answer. Then, when necessary or where necessary, use the calculator to obtain a decimal approximation correct to 2 decimal places for the solution. So, these two problems you're going to have to do the check. And you'll be told on the exam that you will be required to do the check on these logarithmic equations. So in this case here, we got log to the base 2 of x plus 2 minus log to the base 2 of 7 equaling to 3. Alright, in this case here, we need to condense this as a single logarithmic expression here. Here we got a minus sign that tells me the difference of their individual logs. I need to condense that as the log of the quotient, applying the quotient rule. So I'm going to condense that left side as log to the base 2 of, the x plus 2 will be your numerator, the 7 will be your denominator. That's equal to 3. So I got log to the base 2 of the quantity x plus 2 divided by 7 is equal to 3. Now, I only got the log on one side, so I have to use the definition of a logarithm by rewriting this in its equivalent exponential form. So what I'm going to have to do here is this. This base of 2, that's going to be the base. Your 3 will be your exponent. So I'm going to have 2 to the 3rd, and that's going to be equal to that expression right there. So in its equivalent exponential form, This will be 2 to the third equals x plus 2 all over 7. Now 2 to the third power will be 8. It's 2 times 2 times 2. So the 8 is equal to x plus 2 all over 7. Now I need to get rid of that 7 that's in the denominator. Here the x plus 2 is being divided by 7, so the opposite of division is multiplication. So I need to multiply both sides by 7. Okay, that's times 7. And when I do that, 7 times 8 will be 56. And that's equal to, these 7's will divide out. I'm left with simply x plus 2. So I have x plus 2 is equal to 56. Now to get the x by itself, I'm adding 2, so I need to subtract 2 on both sides. That would mean x is equal to 54. So my proposed solution will be x is equal to 54. But with this problem, as I mentioned earlier, you have to do the check. So here's the check. We start with the original equation and replace the x with the 54. So it'll be log to the base 2 of 54 plus 2 minus log to the base 2 of 7 equal to 3. Now if I add the 54 plus 2, I'm going to get 56. So I have log to the base 2 of 56 minus log to the base 2 of 7 equal to 3. Now, the difference of their individual logarithms is the log of the quotient. So I'm applying the quotient rule here. So this will be log to the base 2 of 56 divided by 7 equal to 3. Take 56, divide that by 7, you're going to get 8. So it'll be log to the base 2 of 8 is equal to 3. Now I'm going to write that in its equivalent exponential form. So this will be, the subscript for the 2, for the log will be your base, that's 2 to the third, equals to that 8. Now if you multiply 2 times 2 times 2, which is what 2 to the third is, that would give you 8. So I do have a true statement. So I can conclude that x equals 54 is the solution to that logarithmic equation. Okay. That's how you will solve a logarithmic equation and do the check. Okay, number 18. We have log of 5x plus 1, and that's equal to log of 2x plus 3 plus the log of 2. And I want to solve that logarithmic equation. Now the left side is already condensed as a single logarithm. The right side, I need to condense this. Here I got a plus sign. That tells me I have the sum of their individual logarithms. I need to condense that side as the log of the product. So here I'm going to have to apply the product rule on the right side. So let me go ahead and write down log of 5x plus 1. That's equal to the log of, now I need to condense that as the log of the product. What I'm going to do is write the log of, I'm going to put the 2 in front of 2x plus 3. So here I'm applying the product rule on the right-hand side. Now I'm going to use the one-to-one property. That one-to-one property states this: if you have log to the base b of m equaling to log to the base b of n, then I can say that this expression equals that expression. M is equal to n. That's the one-to-one property. So I'm going to apply that to this particular problem here. So, they're both the same. They're both common logarithms, so I can set the 5x plus 1 to be equal to the 2 times 2x plus 3. Now, the right side, I'm going to use the distributive property here, so I'm going to bring down the 5x plus 1. That's equal to 2 times 2x, that's 4x, plus 2 times 3, that's going to be 6. So I got 5x plus 1 equaling to 4x plus 6. Now, I want to get all the x's on one side and all the numerical terms on the other side. Let's move the 4x over to where the 5x is. I'm going to do that by subtracting 4x on both sides. Now, if I do 5x minus 4x, I'm going to have 1x, or just x. Then plus 1 is equal to 6. And then to get this x by itself, I'm adding 1, so I need to subtract 1 on both sides. So my proposed solution will be x is equal to 5. Now I need to do the check. Using the original equation, I'm going to replace the x with 5. So it'll be the log of 5 times 5 plus 1. That's equal to the log of 2 times 5 plus 3 plus log of 2. Now, bring down the log. 5 times 5, that's 25. 25 plus 1 will be 26. So I have a log of 26 on the left side. That's equal to the log of 2 times 5 will be 10 plus 3 will be 13. So I have log of 13 plus the log of 2. And I'm going to apply the product rule on the right side. The sum of their individual logarithms is the log of the product. So, bring down log of 26 and then condense that as log of 13 times 2. And then if I do 13 times 2, I'm going to get 26. So I have log of 26 equals log of 26. As you can see, the left side and the right side are the same. That checks. So I can conclude that x equals 5 is the solution to that logarithmic equation. Okay, so that's problem number 18, where you have to do the solving and the check. And finally, problem number 19. How long will it take for an investment of $2,500 to grow to $5,000 if the annual interest rate is 7%? And the interest is compounded continuously. Round the answer to one decimal place. Okay, so let's look at what's given to us in problem number 19. We know we have an investment of $2,500. That's going to be your principal, or P. We want it to grow to $5,000. That's the amount that we want to obtain. The interest rate is 7%. Now 7% as a decimal, keep in mind, that's 0.07. You can take 7 and divide that by 100, and that will give you the decimal value of that percent. and it's compounded continuously, so we must use this formula. A is equal to P times e to the RT. A is equal to P times e to the RT. And then substitute those values into that formula. We're finding out what T is. Just ask how long. So the time is what we're looking for. Now your A is 5,000, so we have 5,000 equaling to P, that's 2,500. E is just E. R is 0.07 times T. So now we have an exponential equation that we're going to need to solve for T. Alright, in this case here we need to get this e to the 0.07t by itself. It's being multiplied by 2,500, so we're going to divide both sides by 2,500. So now on the right side I'm going to have e to the 0.07t. That's equal to 5,000 divided by 2,500. That's going to be 2. I also know something else. E and ln are inverses of each other, so it'll be best to take the natural logarithm on both sides. Now on the left side I have ln of 2 equal to, now ln of e to whatever that exponent is that exponent. So ln of e to the 0.07t will be 0.07t. And then we can go ahead and solve for t. It's being multiplied by 0.07, so we need to divide both sides by 0.07. So t will be this, using our graphing calculator. Press the ln key and then type in 2, close your parentheses around the 2 because you only want the ln of 2, and then that's divided by 0.07, and then hit equal. Now to one decimal place it will be 9.9. So it will take approximately 9.9 years for a $2,500 investment to go to $5,000 at 7% compounded continuously. Okay? So that would be basically what you're going to see on your fourth exam, which will cover only Chapter 4. Now, do feel free to watch this video as much as you need to in order to get an understanding of how each of these problems were done. Keep in mind you'll have a help sheet that will assist you with all of these problems on this exam. And also feel free to email me if you have any questions about any of these particular problems that I went over in this particular video.